today's lesson, we are going to learn about Unit 6, Day 1, Graph and Model Exponential Growth Functions. Our learning targets for today are for you to be able to say, I can write an exponential function from a table, I can graph an exponential growth function using a PFRST table, describe the transformation of an exponential function from its parent, and identify the domain and range. I can use exponential growth models to make predictions about real-world occurrences, as well as find the ending balances of accounts given the interest rate and how often the interest is compounded. That is a lot that we are going to be doing in this lesson. Let's go ahead and get started by talking about what an exponential function's structure looks like. First of all, this is the most basic form of an exponential function. Y is equal to A times B raised to the x power. You're going to see that your exponent is going to be the x. The A value, this is your starting amount whenever x is equal to 0. So if you think about it, if x is equal to 0, then that would mean that your y value is going to be A. So 0A is your y-intercept, and that occurs only if there is nothing that you are adding on the outside of our function. So this is 0A is our y-intercept, and it represents our starting amount. And once again, this happens whenever you are not having any addition. So you just see y is equal to A times B to the x. B, on the other hand, this is how much your graph is growing or decaying over time. It is your growth or decay factor. So that's your B value. It is what you are multiplying y by in a table of values. So you're going to see a table of values that we're going to be analyzing, and your B value is going to be the number that we're multiplying every single time to get to the next number. For these types of problems in this structure of y is equal to A times B to the x, I want you to notice that there is an A value, but this is without H and K to start. So we are talking about this without H and K. And what you just see here is just a number times a B, and B is going to be what we call a base. Our A value is going to be very similar in structure to what an A value has always been for us, but we're going to just explore really quick, in general, what would happen if you could just have an exponential growth and an exponential K where our A value is positive. So an exponential growth model in the form of y is equal to A times B to the x power is considered exponential growth if your B value is bigger than 1 and A is greater than 0. So what this means is that your B value, your base, is a number that's bigger than 1 and you have a positive A value. What I want you to always note is that your A value is positive and your B value is also positive, but B is larger than 1. More generally, a base is not allowed to equal a negative number. So therefore, you'll see that your base is going to be always a positive value. So this is considered exponential growth. Exponential decay, what that looks like is y is equal to A times B to the x, still the same exact format, but this time our B value is in between 0 and 1. So it's going to be some kind of fraction, some type of smaller number, and our A value once again is going to be greater than 0. So what we see here is A is positive and B is a smaller number. That is between 0 and 1. And when A is negative, we are going to explore that, and it changes our growth and decay categories a little bit, but we're going to talk about that later on in our lessons and into the unit. So in example number 1, what we want to do is we want to determine the equation of the table. So let's go ahead and make that clear really quick. So we want to determine the equation from the table. So what we want to do is we want to look at our x values and our y values. And whenever we are identifying an a value, remember that an a value happens whenever our x value is 0. And in letter A, we can see that when x is 0, our function is 2. This means that our a value is 2. So a is equal to the number 2. So when we write an equation, we want it to be in that form of y is equal to a times b to the x power to start. So far I have y is equal to 2. And now I need to identify what my multiplier is, what my b value is. Sometimes this is called a multiplier. A base is called a multiplier. And once again, this multiplier is always positive. So the base is always positive. It is never negative. It is never 0 as well. So the base is always a positive number. So that would be something to definitely write down. And it is that number that you're multiplying by each time in order to get to the next number. So what I want you to notice right here is that if we're going from 2 to 12 to 72, from 2 to 12 to 72 to 432, what are we doing each time? So what we're multiplying by each time is the number 6. So 2 times 6 is 12, 12 times 6 is 72, and I'm pretty sure that if we were to take out a calculator and take 72 and multiply that by 6, we're going to end up with 432. So every single time we are multiplying by 6. So therefore, I'm going to be multiplying 2 times 6, and it's going to be raised to the x power. Because 6 is greater than 1, this is considered exponential growth. And our reason is that the base is bigger than 1. And that is our reason. So let's go ahead and look at letter B. For letter B, we want to identify our a value, and our a value happens whenever x is equal to 0, so that I can see right away that a is automatically 27. So I'm going to write that a is equal to 27. That's what I automatically know. And just like over here, what we were multiplying by each time, that's our b value. So I need to figure out what I'm multiplying by. And what I see is that my numbers are going down. They are decreasing each time in order to get to the next number. So in order to go from 243 to 81 to 27 to 9 to 3, it appears as if we are dividing by 3 each time. But remember that this is supposed to be a multiplier. So remember that to divide by 3 means to multiply by the reciprocal. So that is like multiplying by a third. So we are actually multiplying by a third each time, and this right here is our b value. It's whatever you're multiplying by. So therefore, our equation is going to be y is equal to 27 times 1/3 to the x power. This one is going to be exponential decay, and that is because our b value, or our base of 1/3, is smaller than 1, or in between 0 and 1. So therefore, this is considered exponential decay. Letter C is a little bit different because unlike the other two tables, I can quickly identify what my a value is in the other tables, but this time I don't have a 0. So instead, I need to hop into what our multiplier is. So going to the next number, to go from 25 to 125 and 125 to 625, it appears that we are multiplying by 5 each time to get to the next number. So I know that this right here, this 5, is my base. So now in order to go backwards, so I need to calculate when x is equal to 1, and then once again when x is equal to 0, I need to, instead of multiplying by 5, I need to divide by 5. And 25 divided by 5 is 5. And 5 divided by 5 is 1. So in this case, my a value is going to be 1. So a is equal to 1. And we already know that my base is equal to 5 this time. So therefore, my equation is y is equal to just 5 to the x power. If you want, you can write this as y equals 1 times 5 to the x power, but you do not need to have the 1 in front whenever that a value is 1. In this case, once again, this is going to be exponential to growth, and that is because our base is bigger than 1. And so that's what we would write down for our explanation. So what we want to do in example number 2 is we want to create a table, create the table given the following equations. So then we want to determine if the equation represents exponential growth or decay. So looking at letter A, I have f of x is equal to 8 times 2 to the x power. And whenever we set up a table of values, we just typically let x equal -2, -1, 0, 1, and 2. So those are the values that I'm going to put into either a calculator or directly into this function. So let's go ahead and start. We have, this is 8 times 2 to the -2nd. So that is 8 times basically 1 over 2 squared, which is 4, and 8 over 4 is 2. Next, we have 8 times 2 to the -1st power, which equals 8 times 1 over 2, and half of 8 is 4. And what we know about this is that according to this multiplier, I know that my multiplier is 2, so notice that I'm multiplying by 2 each time in order to get to the next number. So I can continue that pattern. 4 times 2 is 8, and notice that that's my a value, 0, 8. And then if I multiply that by 2, I can get 16, and 16 times 2 is 32. So that is just filling out our table using our pattern. This is considered exponential growth, and the reason why it's exponential growth is simply because our base of 2 is greater than 1. Let's go ahead and look at letter B. In letter B, I know that I'm going to let x equal -2, -1, 0, 1, and 2. And if you want, you can put 20 directly into the middle. And we have our multiplier. Our multiplier is 1/2. So I'm going to be multiplying 1/2 to get to the next number. Half of 20 is 10, and half of 10 is 5. But how do you go the other way? Well, it's going to be the inverse operation. So instead of multiplying, we divided to go backwards. So instead of multiplying by 1/2, we divide by 1/2. And instead of multiplying or dividing by 1/2, we're going to multiply by the reciprocal. So we're going to double. So instead of multiplying by 1/2, we'll divide by 1/2 or multiply by 2, making this 40. And the number before that is 80. So this is, of course, as x is getting bigger, we see that our numbers are getting smaller. So this is exponential decay. And we can see that from our base, and that's because our base of 1/2 is between 0 and 1. All right, let's go ahead and move on to the next page. On the next page, we're going to actually start graphing exponential functions and their features. So let's go ahead and check out what those features look like. So the first thing that I want you to bring your attention to is a reminder of the term asymptote. And we've talked about the word asymptote this year. And remember that an asymptote is a very special line that the graph approaches more and more closely, but it does not cross. An asymptote is a line that we draw as a dashed line. So it needs to be a dashed line. So that's really, really important. And our graph is going to approach this asymptote, but not cross it. So the parent function for an exponential growth function looks like this. It is y is equal to b to the x power. Now, all exponential growth functions are going to appear to be the same. And the only thing that changes is whatever our b value is. So its exponential growth, or a parent function for exponential growth, is in the form of y is equal to b to the x power. Our b value needs to be greater than 1. Notice my a value is an invisible number 1. And this is called the family of exponential growth functions, and it has a base of b. The general shape is what you can see right here. And what we have is it's an arrow that is increasing, and it's going to be pointing up, and it's an arrow that is pointing to the left, and it's approaching an asymptote. And I know it's not drawn in here, so what I want to bring your attention to is right here on the x-axis is an asymptote. And this asymptote is at the line y is equal to 0, and it's at y equals 0 because this is actually based on the k value. So eventually we're going to be adding numbers on the outside of this function, and it's going to be the number that we are adding on the outside. It's not going to be in the exponent position. There are 2 points that always cross through this function, regardless of whatever our base is. If it's exponential growth, it's going to cross through the ordered pairs 0, 1, and 1b. So these are our ordered pairs that I need you to know. So if we are creating a PFRST table, those are going to be the only ordered pairs that you need to make sure that you are plotting. So we only plot 2 points, unlike our other functions where we had many points. Notice that the graph rises from left to right going through these points. So it's going to be approaching the asymptote, going through those points, and then increasing. So knowing that it's like a sideways J or like a leaning curve, that will be a really good thing. And then I also want to bring your attention, just like we had before, we want this arrow to be approaching the asymptote, so that arrow needs to be in the swim lane in between our two, like our lines right there, in order to show that it is genuinely approaching. So the x-axis is the asymptote in this graph, and that is just for the parent function. Our domain is going to be all real numbers, and the reason why it is all real numbers is because we have an arrow that is pointing to the left and an arrow that is pointing to the right, but the range actually has a restriction on it. This asymptote is a line that this function approaches but does not cross. Notice that our graph is above it, so therefore our range is going to be all values of y that are greater than 0, and our asymptote and our range value are always going to be the same, and this number is always going to be our k value. Likewise, you can also write this as 0 to infinity. If our graph was had a reflection, we would go from negative infinity up to 0. But this is just our key information to our parent function. And our asymptote, once again, is located at y equals 0. And once again, this is our k value. So our k value affects our asymptote as well as our range, which is very familiar information that we have seen already before in other functions. So we're going to talk about the transformations of our parent function. So we're starting about the graph, or talking about the graph y is equal to a times b to the x, and y is equal to a times b raised to the x minus h power. So x minus h, this is the exponent. There's going to be a number that's going to be connected to the exponent, and that's going to be your h value. And k is going to be a number that's in line with the other numbers, and it's being added or subtracted on the outside. So the transformations for a is going to be consistent, just like we have seen every single time. So our a value, if a is equal to a negative number, what you're going to see is that you will have a reflection across the x-axis. And if you see that the absolute value of a is greater than 1, then we will have a vertical stretch by a factor of a. And what you'll see is that our graph is going to be kind of increasing at a pretty decent rate when it comes to our a value. Likewise, if you see that a is in between 0 and 1, the absolute value of A is in between 0 and 1, we are going to call that a vertical shrink by a factor of A. And that is a very familiar thing that we have talked about a lot this school year. Please also note that if there is no transformation or translation, meaning if there's no H and K, the y-intercept will occur at 0A instead of at 0, 1. So please just know that if you see that you're not adding or subtracting anything. And then when it comes to translation, we can translate the graph horizontally H units to the left or right. And this, once again, is always the opposite of what you see. And it's going to be an H value that's connected to the exponent. And then we can translate the graph vertically, K units. And that's going to be up or down. And remember that your K value is the number that you're adding on the outside, and this is exactly what you see. So this is the language that we have talked about many times over this school year. So whenever it comes to graphing exponential functions, these are the following steps. So what we want to do is we want to create a PFRST table, very similar to what we have done before. Our parent function ordered pairs, once again, are 0, 1, and 1b. So those are going to be our ordered pairs that we are going to use, and these are the values that I need you to have memorized. So that b value is always your base, and that number is going to change. Step 2 is going to be to identify and graph the horizontal asymptote, which, remember, this is at y is equal to k. Then we're going to plot our points from the final column of the table, and then we're going to identify our domain and range. So here we go. Let's start off with example number 3. It says, graph the following functions and state the domain, range, and asymptote. So looking at letter A, we have y is equal to 1/4 times 6 to the x power. One of the things that I like to do is I like to identify everything. I like to identify my A, my B, my H, my K, and I can see that my A value is 1/4, B is 6, and H is 0 and K is 0 because we're not adding anything in the exponent and we're not adding anything on the outside. So therefore my asymptote is located at y equals 0. So I can actually draw that in right away. So now what I'm going to do is I'm going to create a PFRST table. So remember that we're just plotting two ordered pairs and remembering what shape we are using. So this is P, F, R, S, and T. So my parent function ordered pairs are 0, 1, and 1 comma my B value, and my B value is 6. In terms of a reflection, my A value is positive, so I have none. And my shrink, I'm actually multiplying by 1/4 because I'm going to have a vertical shrink by a factor of 1/4. So all of my y values are going to be multiplied by a 4th this time. So I have 0 and 1 times a 4th is 1/4. And 1 and 6 times 1/4 is 6/4, which is 1.5. I am not adding or subtracting anything, so therefore the last set of ordered pairs are the ones that I'm going to plot. So I am going to plot 0, 1/4, and it's going to be an approximation of where that is located, and 1, 1.5. So that point's about right here. And I'm going to connect these 2 points, and I'm just going to approximate where this is located, making sure that this function is approaching, but not touching or crossing the asymptote. Our domain is automatically all real numbers because I have an arrow pointing to the left and an arrow pointing to the right. And because my graph is above the asymptote, I am going to say that my range is going from 0 to infinity. I want you to note that because there is no equal to symbol up here, we're using a soft bracket, not a hard bracket. It is not crossing the asymptote. So you really want to make sure that you have 2 parentheses and not a bracket and a parenthesis. Let's go ahead and look at letter B. In letter B, I am going to identify that my A value is 2, my B value is 3, my H is the opposite of what I see, which is 2, and my K value is negative 2, which means that my asymptote is located at y equals negative 2. So I'm going to draw in my asymptote at y equals negative 2. So next, I'm going to create my table of values, parent function, reflection, stretch translation table. And my ordered pairs are 0, 1, and 1 comma my B value. And my B value in this case is 3. In this problem, my A value is positive, so I do not have a reflection. When it comes to stretch shrink, my A value is not 1, so therefore I'm going to multiply all Y values by the number 2. And 1 times 2 is 2. 3 times 2 is 6. So my ordered pairs are 0, 2, and 1, 6. When it comes to translation, my H is 2. That's the opposite of what I see right here. So all of my X values will be increased by 2. And then my K value is negative 2. So all of my Y values will be decreased by 2. So 0 plus 2 is 2. 2 minus 2 is 0. 1 plus 2 is 3. 6 minus 2 is 4. So these are my ordered pairs that I'm going to be plotting. So let's go ahead and plot 2, 0 and 3, 4. And I'm going to make sure that my graph is approaching the asymptote. And here's what my graph looks like. And all you can do is just the best that you can in terms of graphing this, because I'm only giving you 2 points. Our domain is going to be all real numbers. And our range, because our graph is above the asymptote, we are starting at negative 2 and approaching 0 with soft brackets around it. You can also write this as y is greater than negative 2 if you like working with inequalities instead. All right, let's go ahead and move on to the next problem. This problem is going to be a team question, and we're going to do this problem the next time that I see you. So let's go ahead and look at our next, and we also have a solo, and so that'll be something that we are going to work on the next time that I see you. If you would like to go ahead and do those problems on your own and be prepared for the next time that we get together, then I think that that is perfectly fine with me. So moving on, we're going to start talking about how this is useful in real life. And out of all the things that you're going to learn in Algebra 2 with trig, exponentials are probably the most useful that you're going to actually use outside of a math class. So when it comes to an exponential growth model, it happens when a real life quantity increases by a fixed percent each year or some other time period. Most of the time in our class, we're working with years. So I want you just to keep that in mind. So it is where a real life quantity increases by a fixed percent each year. When that happens, the amount y of the quantity after t years can be modeled by y is equal to a times 1 plus r to the t power. So what I want you to notice about this model is that it's very similar in structure to the form of y is equal to a times b to the x power. And notice that this is a growth model, and we have 1 plus a number. And remember that your base needed to be bigger than 1. So it's very, very similar in structure to this model. So that's what this is just like. And we use this type of model for all problems that are not bank questions. And you'll see what bank questions look like. It'll be for everything else, like a population is growing, or the amount that an investment is worth, meaning like you've purchased a house, how much has your house increased by, etc. So I want you to know that in this model, the A value is your initial amount. It's your starting value. Your R value, well, that is the number that is your rate. It is a percent increase, and we always write it as a decimal. So if you are ever given a percent, you take that percent, divide it by 100, and that will equal the decimal that we are interested in. And we always represent it with the letter R. And then 1 plus R, that whole base right here, is considered our B value. It is our growth factor. So it is the entire base of 1 plus our growth factor. 1 plus R, that's considered our base, our growth factor. So in example 4, it says, in the last 12 years, an initial population of 38 buffalo in a state grew by about 7% per year. Write an exponential growth model giving the n or the number n buffalo after t years. Whenever you see a model, we always require 2 variables to model a problem. It is very important that you know that a model always has 2 variables. And in this problem, I know that my initial amount is going to be basically my A value. And my A value in this problem is 38 buffalo. And my R value, that's my rate. And I know that this is 7%. So I can take 7%, divided it by 100%, and that's going to give me 0.07. Now, you do not have to show me this work to come up with your rate. If you know that 7% is 0.07, go straight there. But I want you to be very careful. A lot of students will simply say 0.7, and that means 70%. So please be very, very careful. So now I'm going to talk about our model. So we know that we have y is equal to a times 1 plus r raised to the t power, but this time we want the number of buffalo. So we're going to write this as n equals a times 1 plus r, and it's still t years. So my model is going to be n equals 38 times 1 plus 0.07 to the t power. Now, I can clean this up, and I'm expecting you to do the same. All you have to do is add those 2 numbers together, and then you have your official model. So our official model is going to be n is equal to 38 times 1.07 to the t power. This is our model. A model always has 2 variables, and it always has a simplified base. So now what we're going to do is we're going to identify the initial amount, the growth factor, and the percent increase. So our initial amount, we already know. So our initial amount, I'm actually going to write this as initial amount, we already know is 38 buffalo. Our growth factor, remember that's the base of our model, and our base of our model is 1.07. So our growth factor is 1.07. So it is the full base. So that is something I want you to note, that our growth factor is a full base. And then finally, we have our percent increase, and our percent increase, well, that's just 7%. And there is a way for you to come up with that. If you ever are in a situation where they give you the model without any context, the way that you can find your percent increase is you're going to basically do 1 minus r is equal to your percent. So let's say that we have 1 plus 0.07, and 1 minus b is equal to your percent. Here we go. So I'm going to go 1 minus, how about this? Let's change this up. Sorry, I wrote it out incorrectly. We're going to write this as our base minus 1 will equal our percent. So I'm going to write 1.07 minus 1 is going to be equal to 0.07, and I can write this as 7%. So that's how you can find what your R value is. And this is important for our homework that we're going to be doing. So you'll take your base and subtract it from 1, and that'll tell you what your percent or your rate is going to be. So letter C is asking us about How many buffalo were there in the park after 7 years? So let's go ahead and take a moment to actually graph this function. Or before we do that, we can actually calculate this by hand, and we'll graph in letter D. So about how many buffalo were there in the park after 7 years? What this means is let T equal 7. So I'm going to write N is equal to 38 times 1.07, and I'm going to raise it to the 7th power. So if you need to take a moment really quick to grab yourself a calculator, you are more than welcome to do that. And I'm going to do the same. And so in my calculator, all I'm going to do is I'm going to write 38 or type in 38 times 1.07. I'm going to close my parentheses, and then most calculators has some sort of caret button. So I'm going to raise it to the 7th power. And because we're talking about full buffalo, I'm going to say that that's about 61 buffalo. We don't want to say 61.02 buffalo because that's really awkward. So we're just going to write 61 buffalo. And because this problem has context, I'm going to be looking for word answers. For letter D, we want to now finally graph this model. So we know how to graph models. We create a PFRST table. So I'm going to write 0, 1, and 1 comma 1.07. In this problem, I do not have a reflection, but I do have a stretch. I'm going to multiply all y values by 38, which is our a value. So all I'm doing is graphing this model right here. And I end up with 0, 38, and 1 comma 1.07 times 38. Well, that's what I'm going to have to put into my calculator. And when I do that, I end up with 40.6, or you can write it as 40.7. And any way that you round it is perfectly fine with me as long as it's accurate. We want to make sure that it makes sense for our problem. I mean, we're approximating, so it doesn't really matter. We're not adding or subtracting on the outside, so these ordered pairs are the only ones that we're going to be plotting. And let's go ahead and do that. My asymptote in this case, because I'm not adding or subtracting anything on the outside, my asymptote is going to be located at y is equal to 0 or n is equal to 0. And I'm going to start by plotting some points that I already know. So in addition to these points down here, I know 0, 38, I know 1 and 40.7, but you know what I also know? I know that if I let t equal 7, I'll get 61, and I found that in letter C. So because of that, I'm going to plot all 3 of those points. So let's go ahead and plot 0, 38. So this is going to be an approximation. And then I'm going to plot 1, 40.7. And then I'll plot 7, 61. So I'll just have this increasing. I don't have an arrow going down because of the fact that I'm working with context and we do not want to have negative years or negative number of buffalo. So we want to figure out or use the graph to estimate the year when there were about 53 buffalo. So we're using the graph to estimate. So 53 is going to be somewhere about right here. So that's going to be somewhere in this amount. So we're looking at 4 years, 5 years, 6 years. So let's go ahead and try 4 years. So I'm going to let t equal 4. And so I'm going to write n is equal to 38 times 1.07 to the 4th power. And I'm going to see what number I end up getting. So 38 times 1.07 raised to the 4th power, you get 49.81. So that's about 50 buffalo, which is pretty close to 53, but I'm just gonna check when t is equal to 5, just to see if that becomes too big or which one's closer to 53. So I'm gonna write 38 times 1.07 to the 5th power. So I'm going to write 38 or type in 38 times 1.07 raised to the 5th power. And I end up getting 53.29. So that's about 53 buffalo. And I would say that after how many years would we get to about 53 buffalo? That's going to be after 5 years. So if you see a problem like that in your homework, show some support as to how you were able to come up with that answer. All right, we have one more page. Let's go ahead and flip. And these are called bank questions, compound interest questions. So when it comes to these types of bank questions, if you remember, I said that we have an exponential growth model when we are not using a bank versus ones that we are. So these are known as bank questions. It's where you are investing a certain amount into an account and you're watching that amount grow. So compound interest is something that you may have heard about in your experience. Maybe you've never necessarily studied it before, maybe you have, but essentially, in general, compound interest is the interest that is paid on an investment called the principal. And on previously earned interest. So you're not just investing and getting money back for your investment, but every single month, wherever that initial amount is at the beginning of that month or at the beginning of that day or that beginning of that year, depending on the time that we're talking about, you're going to receive more and more interest on that. This is how credit cards make their money. So if you don't pay your balance off at the end of the month, you have to pay not just interest on how much you initially paid with that credit card, but however much is remaining on that credit card as well. So it says, consider an initial principal P that is deposited. So an initial amount of money is deposited into an account that pays interest at an annual rate. So that annual rate is denoted as the letter R. And once again, we represent that R value as a decimal. And it is going to be compounded n times per year. The amount in the account, the amount A in the account after T years is given by the formula A is equal to P times 1 plus R divided by N raised to the NT power. So I want you to notice that P is your initial amount. It's how much you invested. 1 plus R divided by N is a very fancy base that's going to be bigger than 1. And you're raising it to the NT power. So N, once again, is how often interest is being compounded. So it all depends on the language of the problem. If you see the word annually, we're going to let N equal 1 because interest is being compounded one time a year. If you see the language of semi-annually, we're going to let N equal 2. That means that interest is compounded twice a year. If you see the word quarterly, think 4 quarters in $1. 4 times a year, we're going to let N equal 4. If you see that interest is compounded monthly, there are 12 months in a year. So we let N equal 12. And if you see daily, we're going to assume always that it is not a leap year, and we let N equal 365. So these are numbers that I need you to pay attention to whenever you are working with this type of problem. So in example number 5, it says you deposit $2,900 in an account. So you deposit $2,900 in an account that pays 3.5% annual interest. So what we know so far is we know that our principal and how much we're investing is $2,900. And our rate, we know that that's 3.5%, and we can write that as 0.035. Remember, you can also go 3.5 divided by 100 to come up with that number. We are being asked to find the ending balance. So we need to find our amount in the account after 5 years. So we're letting T equal 5. If the interest is compounded monthly, annually, and daily. So letter A is asking us to compound interest monthly. So that means we're going to let n equal 12. So there's not a tremendous amount of work to show with this. It's just a matter of putting it into your calculator correctly. So I'm going to write that A is equal to 2,900 times 1 plus R, and R is 0.035 divided by N, which is 12, raised to the 12 times 5 power. So that is the NT power. Now, I would recommend strongly using your calculator to your advantage and writing this as A is equal to 2,900 times 1 plus 0.035 divided by 12 raised to the 12 times 5 is 60. And I would calculate just the exponent just to make sure that you get this answer correct. And now I'm going to put this whole thing into my calculator directly as I see it. So that is going to be 2,900 times parentheses 1 plus 0.035 divided by 12, close the parentheses, and now raise it to the 60th power. If you do that, if you calculate this exponent separately, you'll get the right answer every time. If you don't, then the calculator does a funky order of operations and you won't get the right answer. So rounding this to money, please note that this is going to have a dollar symbol in front. A lot of times kids will put their dollar symbol second, and that is incorrect. So this is $3,453.73. So we're always going to make our answer look like money. So I ran out of space. I'm just going to write like a little error right here that's where this goes. I ran out of space for that. All right, let's go ahead and look at letter B. For letter B, we are compounding interest annually this time. So our initial investment is $2,900. Our rate is 0.035. This time interest is being compounded annually, so we're letting n equal 1, and we still have our time being 5 years. So I'm going to write A is equal to 2,900 times 1 plus 0.035 divided by 1 raised to the 1 times 5 power. So I'm going to put into my calculator A is equal to 2,900 times 1 plus, and anything divided by 1 is just itself, 0.035. And 1 times 5, once again, is just itself, so I'm going to raise it to the 5th power. So in my calculator, I'm going to write in 2,900 times 1 plus 0.035 raised to the 5th power. So I'm just putting that into my calculator exactly as I see it. And my annual amount, my final amount is going to be dollar symbol first, $3,444.29. I'm going to leave the solo question for you to try on your own, and we'll come back together next time that I see you. And now we have finally our last example. And in example number 6, it's asking us this time, how much must be deposited? Please pay attention to what the question is asking you. How much must be deposited, which means they're asking you to find P this time. We need to find our principal. How much must be deposited now in an account paying 8% annual interest that is compounded quarterly to have a final balance of $1,000 after 10 years. So we need to find how much is deposited. So that's our P value. I don't know what that is. I do know my rate is 0.08. I do know that interest is quarterly, so therefore, compounded quarterly, so n equals 4. My time in this case is 10 years, and my final amount is $1,000 this time. So I need to find what P is, so I'm going to put all of these values directly into our formula. So I have 1,000 equals P times 1 plus 0.08 divided by 4 raised to the 4 times 10 power. So what I want you to recognize here is that this is a very fancy number. This is P times a number. And all I need to do on both sides is I just need to divide both sides by this number. So I'm going to divide both sides by 1 plus 0.08 divided by 4, and I can change that to the 40th power. So this is P times a crazy number, but this is just a single number, and we're just dividing both sides by that number. 1 plus 0.08 divided by 4 raised to the 40th power. So I'm just using my good math skills to just recognize that now by doing this, these two numbers cancel away, leaving us with just P. And this was all calculator work, so you want to be really careful with how you put this into your calculator. This is 1,000 divided by parentheses, and then I'm going to do parentheses again to establish that this is my entire denominator that's going to include that 40 at the bottom. 1 plus 0.08 divided by 4, close the parentheses, raise it to the 40th power, close it one more time to establish that I have finished putting in my denominator, enter, and that number should be a lot smaller than the investment. So if you were to invest $452.89 into an account that's paying 8% annual interest compounded quarterly, you'll end up with $1,000 after those 10 years. And that is the end of today's lesson. If you have any questions over anything that I talked about today, please feel free to reach out to me. Otherwise, I hope you have a wonderful day.